working in JICE from Japan, and I'm working on this work with Viennot, who is also in the room. So we decided to study a famous game, Mastermind. So I guess most of you already know this game. Since I was lazy to introduce the game, I just copy-paste from Wikipedia. So the picture is also from Wikipedia. Basically, a Mastermind is a code-breaking game for 2 players. There is one player, which is at the bottom here, which will choose a secret code, and the second player will need to decode here. So in the short introduction of Mastermind, I want to highlight one keyword, which is 2 players. So it should be a 2-player game. So in these 2 players, there are the first player is a code maker, so it makes only one move. At the beginning of the game, he has to choose a secret code. So a code in the traditional game, so the one which is presented here, there are different versions which have been solved, but this one is a classical one. There are 4 pegs, and you need to choose a code of 4 pegs among 6 colors. So you can have a 6 power 4 combination, which is 1296. And the second player, so at the beginning, the code maker chooses one code, and it doesn't make any other move later. The code breaker needs to discover this secret code. So it will make successive guesses. A guess is also a sequence of 4 pegs chosen among the 6 colors. And after each guess, the code breaker will receive some feedback to know how much he is close to the real solution. So we receive 2 feedback, which is the number of correct pegs, so which is exactly correct, the same color, the same position, and the second number, which is the number of correct color, but at the incorrect position. So if some of you doesn't know the game, I will depict one execution of the game. So at the top, it is where the code maker will choose a code. So I choose one code, so green, blue, red, and pink. Yes?
Are multiple pegs with the same colors allowed?
Yes. So there is a variation of the game, which is called, I think, coin or AB game, I think, where you cannot have 2 times the same color. So here in the classical Mastermind game, you can have 4 times the same color if you want. So there is no restriction. So 6 color for the first peg, 6 color for the second peg, etc. So in total 6 power 4 code. So initially he chooses one code and then he hides so that the second player cannot see. So since I want to be able to see, I will not hide for the presentation. The one who is trying to guess, to find the code, will propose one guess. So for example, 2 yellow and 2 blue, and will receive feedback. So the code maker will compare the secret code with the guess, and here you can check that there is 0 peg which are identical. On the other side, there is one blue peg, or this one, one of them, which is not at the correct position. So here it's position 3 or 4, and in the real code, there is a blue peg at position 2. So the feedback that will be received in this case is 0 peg which are correct, and 1 peg which is incorrect. So even if there are 2 blue here, since there is only 1 blue in the secret code, there will be only one for the feedback. So based on this feedback, the second player will try to propose a new guess. So what human player do is we will use this information, and maybe I will think that this yellow here, of course I don't know if it is the yellow or the blue, which is not at the correct position. So maybe I will think the yellow is at the incorrect position. I will try to put it there and propose some other colors to complete the code. So here again I will receive some feedback. There is 1 red which is at correct position and 1 pink which is incorrect position, so etc. I will not explain everything, but we can continue like this. And at the end, after a few steps, so here it's 1, 2, 3, 4, 5, 6 steps, we finally reach the correct solution and the game is over. So here what is interesting is to count how many steps we need. So it is a metric I will use in the analysis, is how many steps to solve the game, so to find the secret code. So I said the goal for the code breaker is to find the solution as quickly as possible. But there are different meaning or different interpretation of as quickly as possible. So first, so this game has been heavily studied in the literature, And the first things people were interested is what I call best worst case. So in 77, Knut proved that for this version of the game, the worst case is 5. So there is a strategy, he proposed a strategy, so that whatever the code which is chosen, he will find the secret code in at most 5 steps. So it was proven quite early. The proof is not very difficult. It is easy to prove that you cannot do it with 4 steps, only 4 steps, because the branch and the game tree will not be large enough to have enough leaf to take all the code, and he just give one solution for 5. After, people were interested at the best average case. So assuming that the code is chosen randomly, uniformly randomly, what is the best strategy that you can do? And much later, so it took 16 years later, Koyama and Lai proved that the best strategy need an average of 4.34 steps, guesses, to find the solution. So which is interesting, in this solution, the worst case is 6. So there is it is not possible to have both optimality at the same time. So after solving this problem, people try to generalize. So there are many generalizations which are possible for Mastermind. So trivial generalization is changing the size of the game. So you can increase, you can study different number of pegs, you can change the number of pegs, change the number of colors. So I highlight 5 and 8, which is also a common version which is sold, that you can buy. And for 5 peg and 8 color, as far as I know, nobody has ever computed the best average case. So even these two cases, worst case and average case, are still open for some cases. So there are other ways to generalize. Some people were interested to find generic result instead of having just one result, so one value. Is if you fix the number of pegs, let's say you fix only to 2 pegs, and you take any number of color. So some people, you can find the reference in the paper, give the exact result. So it is a result, of course, which depends on the number of color. You can also, more recently, some people study when you have a large number of pegs. So this time it's not an exact result anymore, it is more like asymptotic result. So they prove that you need roughly n log n guesses to solve the game. And there are also many other generalizations that you can do. So in all of these cases, people forget that the game is a 2-player game. So they study only one player. They study the strategy of the code breaker, so of the guy who is supposed to break the game. So what we wanted to do is to see, so that's what I said, what about the coder? So is it possible for the first player, the one who chooses the code, to choose the code more efficiently? Maybe not choosing the code randomly. So what is the strategy of a coder? In fact, it will be a distribution, probability distribution of all possible code. Usually people take a uniform distribution, but we do not want to restrict to uniform distribution. So we want to take any probability distribution. And what are the consequences for the breaker strategy? If we change the initial distribution of code, what will be the impact on the breaker? So for the worst case, it doesn't change anything. Because even if you change the distribution, the worst case will be the same. But it may change for the average case. And in fact, it is what we computed, and it changed. So we can give some instances where it's changed. So we checked in the literature, and we found only one paper from '82, which, as far as we know, was never cited, and one person, the author, studied a special case where we consider 2-peg and 3-color Mastermind. So he studied this, the optimal strategy for the coder and the breaker for this instance of the game. So I will summarize the result that he obtained for 2 pegs and 3 colors. So just first some simple observation. So for 2 peg and 3 color, you have 9 possible codes. To simplify, I will not use colors anymore, I will use number. So I will use 0, 1, and 2 for colors. So the code are 00, 01, 02, etc. until 22. For this instance of the game, so with 2 peg and 3 color, it is easy to, you can do it by hand. You can find that the worst case is 3, and the average case, the best average case is 2.33. And now if we consider a non-uniform strategy for the coder, it appears that this is the optimal probability distribution. So you should play the code 00 with 1 over 6. So in fact, all code 00, 11, and 22, you should play with the same probability, which is 1 over 6. And the other codes that later I will call B color, because of course they have 2 color, you should play them with probability 1 over 12. So it is not exactly uniform, it is not a uniform strategy. You have two different probabilities. In this case, the best response from the breaker point of view, so in average, the best he can do is 2.42, which is slightly higher than the 2.33. So by using this strategy for the coder, it will increase the average number of steps, average number of guesses required for the breaker. So we can summarize this strategy by observing that there are some obvious class equivalence classes. So we have the unicolor code 00, 11, and 22, which should be played with probability 1 over 6, and the bicolor code that should be played with probability 1 over 12. So how can we obtain this kind of result? And in fact, we wanted to obtain the same result for the classical version of the game, which is with 4 peg and 6 colors. So first, I will briefly explain how we can obtain one way of obtaining the best worst case, one way of obtaining the best average case, and we will see that obtaining this best, so it is what we call Nash equilibrium, because in fact it will be the Nash equilibrium between the two players. We can compute it in a similar way. So to compute the best worst case, so you can, I suppose all of you are familiar with this kind of game tree. So initially, I will consider a node which contains all the possible code. From here, the breaker can choose one of these code, and depending on the code that he will play, we can have many subtrees which are parameterized by the feedback it receives. So if it receives 00, 01, etc., and of course if it receives 30, it means it correctly guessed the code, so it is the end of the computation. Otherwise, we can partition the set of initial code into multiple nodes. So we can execute this progressively. Here, I will concentrate briefly on this node. So in this node, the breaker knows that there are only 3 remaining possible code. So 120, 210, 220. A human player will probably try to play one of these codes. In fact, for some optimal strategy, you need to play some code which are not possible code. Playing a code which is impossible may give you more information. When there are only 3 codes here, so that's why here I put many a row. You cannot a priori restrict to play a next guess which is only a possible code. In this case, it is possible, so I will shrink the tree. Okay. You can build the full game tree from here. Then you can backtrack from the bottom. So if it remains only one code, one possible code, you need one step to find this code. If it's the same. If you already solved, of course, it is 0. You don't need any more steps. So after you can go up, playing this, playing the move 1, 2, 0 will lead to a cost of 2. You can do the same everywhere. And when you have this set of code, you just need to choose what is the best among this one. So it is a mean of the 3 choices, or the 3 edges. So you can do the same everywhere. And after each step, it is a max. So of course, everybody recognizes, you probably guessed from the beginning, you have a mean and max. So it is classical algorithm. And at the end here, I have the value 4. So this was for computing worst case. For computing average case, so I will skip, it is the same tree. We can do exactly the same. The only difference is the operation that we do. So we still have a mean when the breaker is playing, so we need to choose the optimal between multiple leaf. But when we have, when we backtrack the other type of node, we will need to make a sum, and at the end, we need to divide by the number of code. So I will not enter more detail, but what is important here is before previous slide, I had mean and max operation. Now I have mean and sum operation, but it is quite similar operation. For computing Nash equilibrium, we can do the same. So I will assume that this probability distribution is arbitrary, so I don't fix it. And I will compute what we call the generic cost for all possible strategy. And at the end, we will reach a big linear program, and we can solve it to obtain the Nash equilibrium. So still, we can have the same game tree, but this time, instead of having just some number, we will have a set of points, which can be in high dimension, depending on the game. And the operations are more complex. We don't have any more mean, max, or mean sum. We have, the first operation is a Minkowski sum, so it is from algebraic geometry. And the other operation is a union, so we make a union of points. And when we backtrack all of these until the top, we will reach a set of points which in fact correspond to a linear programming problem. And when we solve this one, we obtain the optimal value for the Nash equilibrium and the optimal distribution of probability for the code, the initial codes. So yeah, I don't have so much time, so I will be quick here. So it is interesting because we need some combinatorial geometry. So we have some 2D, 3D, 4D, 5D geometry. So the dimension of the space will depend on the number of equivalence classes we have for the instance we are solving. So it is funny algorithm. At least I have to learn. I was not very familiar with the notion of convex polytope, convex hull, Minkowski, so all of this. So it was interesting to solve. And surprisingly, computing the three possible metrics are very similar. We just have like different operation, but the structure of the code is very similar. So I will go to the result. So here I summarize values which have already been known. So we compute them again, but they already exist, which are for different number of color and different number of peg, what is the optimal average play. So assuming a uniform distribution of code for the coder. Here it's what we obtain for Nash equilibrium. So values which are in red, it is where the values are different from the top table. So it is the cases where the coder can improve his strategy. As you can see, most of the time the improvement is very small. So here, for example, 3.36, and we go only to 3.37. So improvement is very small. Surprisingly, it is not always possible to improve. There are some cases, like here, for example, with 4 peg and 5 color, where the uniform strategy is optimal. So we don't know why. We don't know why. Sometimes we can improve, sometimes we cannot. It is, we don't know how to generalize. And there are still some missing. For example, here we don't have it because it is much more complex to compute compared to the previous one. So some of them we don't have the value. Now this ugly table gives the probability distributions that should be played, the optimal distributions that should be played by the coder. So they are very unclear, so I will give explanation of why. For example, if we take 4 and 3, so which is 4 peg and 3 color, I have only 4 numbers here. Because for this game, so 4 peg and 3 colors, we have only 4 different kind of code. So it is a equivalence classes that I was looking before. So we have the unicolor code, where we have only so 4 times the same color. we have the class of equivalence where we have 3 times one color and another a different color. So it is all of them, etc. So due to the symmetry of the game, all inside one equivalence class, we should play with the same probability. So that's why here, if I take the same example, so for 3, this one, it means we should never play a uniform color. Each of them we should play with probability 1 over 66, same for this one, and we should play this one with probability 1 over 99. Again, on this slide, it doesn't seem very easy to generalize. Sometimes, most of the time, we should not play unicolor code, so it is 0, 0, 0, but not always. There are some cases, let's say, for example, this one, where unicolor code should be played more frequently than other classes. And the last, which is a little bit strange, is this one. We have a continuous set of, and I will reach the last slide for my conclusion. So it was interesting to study Mastermind, even if it is a very, quite old game which has been studied a lot. We can still do something, which was computing Nash equilibrium. And we had some unexpected and somehow non-generalizable results. Since the title of the session was perspective, I added some also perspective, which could be study other game. When we study Mastermind, and after talking with some people, we realized that there are other games which are somehow similar, which is kind of guessing game. So battleship, someone will put random ship and you need to destroy, so you need to find the battleship instead of finding the code. Black box, they have some atoms which are hidden and you need to find the atom. And guess number is just, we talk in the introduction of our paper, so just someone choose a number and the other one has to guess the number. And I will stop here because I spent my 20 minutes.
Thank you very much for the presentation and also for keeping the time schedule.
Okay.
Thank you. Very well, very well. Questions? 1, 2. I start with Ingo, then Peter, and then I give floor to third or even fourth question if they are short.
When I saw your very last page where you emphasized that it is a 2-player game,
Yep.
it might be possible to play Mastermind with 3 players, say 2 code makers. The first code maker makes the first 2 packs, the other one makes the second 2, and they have no interaction.
It is possible.
Yes, simply a proposal for your next research.
We are always happy that you are here, Ingo. That's fantastic. Yeah. Thank you.
I think there are many variations.
Yeah.
I'm not sure it is necessary to invent new variation again, except if it brings something new. But
Yeah.
there are already many games that are still unsolved, so maybe we don't need to invent new game again.
Okay, Peter.
Yes, you have picked your numbers here uniform over the isomorphy classes of instances.
Yes.
Have you proven that that's optimal, or is that an assumption which is so natural that you have inserted in your model?
I'm quite new to game theory, which is not my main research topic. So for me, I don't know everything. I mean, I don't know so much about the literature, but I think there could be more Nash equilibrium, but there is at least one where you play with using this equivalence, with these classes of equivalence. And if there are other Nash equilibrium where you don't play uniformly, I think you cannot have better payoff. I mean, better, or you cannot change intuitively, but I didn't prove it for me.
You haven't proven it.
No, I didn't. I think, so at the beginning I mentioned one paper. I should, this one. I think they prove it inside. Because this notion of equivalence classes, they also use it in the paper. And I think they prove it. I should check carefully.
Do they prove it for this special case or for the general?
So for zero-sum game, 2 players zero-sum game. So for any 2 players zero-sum game.
Okay, last question. If there are no last questions, then I would like to thank the speaker for